This video is a quick introduction to Newton's law of gravitation, and that's the formula we see right here. Newton's law of gravitation is the classical approach to describing the force of gravity between two masses. As it turns out, all masses feel the force of attraction with all other masses, and this force is proportional to the magnitude of the two masses and inversely proportional to the square of the distance between them. We also note that the distance between the masses r means center to center distance, provided the masses are roughly spherical. Now, with the r being squared in the denominator, this means that if the distance between two masses doubles, the force between them would be reduced by a factor of 4. The constant of proportionality in this equation is big G. This is a constant of nature that simply has to be measured, and we'll use the accepted value of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Notice the units on G. If we look at Newton's law of gravitation, we see that these are the correct units to make newtons pop out of the calculation. The meters squared cancel with the square of the separation distance. The kilograms squared cancel with the two factors of kilograms in the numerator, and we're left with newtons. Interestingly, G was first measured in the Cavendish experiment in the late 18th century. G was measured by computing the force of attraction between masses balanced on a torsion pendulum and large fixed masses, and the value obtained was accurate to within 1% of the modern standard. The Cavendish experiment had to be remarkably sensitive because counterintuitively, gravitational force is very small compared to other forces of nature like electromagnetic and nuclear forces. But gravity is responsible for the structure of the universe, from solar systems to galaxies to clusters of galaxies and so on. And the reason gravity takes over at large scales is that electrical forces can be shielded and nuclear forces are extremely short range. For example, the electrical attraction between the moon and the Earth is practically zero because the moon and the Earth are made of neutral atoms. The atoms contain positive and negative charges, but the net charge is zero. Mass, on the other hand, can't be shielded. So these very large masses will experience large gravitational forces over a large distance. To illustrate how small the force of gravity is and to get an appreciation for how sensitive the Cavendish experiment was, we work a quick example. In the example, we're told that in the Cavendish experiment, lead balls with a mass of about 0.73 kilograms sat at a distance of about 30 centimeters from lead balls with a mass of about 158 kilograms. So those large ones are the ones that were fixed in place. The small ones were the ones sitting on that torsion pendulum hanging from a wire. And in the problem, we're asked to compute the force of gravity between a small and large lead ball in the experiment, and then round our answer to two significant digits. So we write down Newton's law of gravitation, and then we're going to plug in big G and the value of the masses, and then the separation distance between the two masses, center to center, is 0.3 meters, just converting to SI units there. So there's all the numbers plugged into Newton's law of gravitation, and when we run the numbers, we get 8.5 times 10 to the negative 8th newtons. So we're talking about forces on the order of hundreds of millionths of newtons. And it's absolutely mind-blowing that this could be measured in the late 1700s. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.